Good afternoon.
Hello.
Okay, I kind of changed my mind a little bit about what I'm going to do today. I wanted to. Oops, I was thinking about doing another test, but I don't know. I feel like I've already got the test we did on Tuesday. Plus, I've got one in the mini lectures as well, a test review, a different one. So I feel like having reviewed two tests is plenty here. So I'm just going to treat today as a Q&A session, and we'll see if anybody has any questions.
I definitely do.
Okay. Okay. Oh, cool. Then let's do it. Let's do the Q&A. All right. Who's first?
Ladies first.
Oh, okay. Oh, aren't you nice, Peter?
Thank you.
All right, Julie, what's up?
Okay, my question is about the synthesis problems, not the first four, but the 5 through 15 that you gave us on the.
In the blue book?
I guess it was in the blue book. I printed it out.
Yeah.
Here the following from aldehydes, ketones, esters, dicarbonyls, or APN saturated compound. And I guess my big question was, I only really had problems on two of them, and I still don't know how I would know which was number 7 and number 9.
Okay, but let me take a squiz. I gotta get to it.
Okay.
All right, let's have a look. Here we go. What page is it on, Julie?
25, it says here.
Okay, shouldn't be too hard for me to find. Okay, here we go. All right, so 7.
So yeah, 7 and 9, but I guess my real overall question was, when you're looking at these and you see all these in front of you, how would you know where to start? There must be a way to be able to know, and I'm sure you've told us in other ways, but I've just looked at it, it just was overwhelming. Like, how would I know where to start?
I know, it's pretty scary, isn't it? All right.
Yeah.
Now there's actually four reactions really going on here. I know this is a little bit more than what I went through in the class. But if you've got let's look at what the products are, and I'll just show you what they, I'll show you what they correspond to reaction-wise, okay? So if the product is this kind of thing, then it's an aldol. Aldol or possibly a crossed aldol. All right, you with me so far? Julie, is that right?
Yeah.
Okay. If the product looks like this, then it's a glycine or a cross glycine. Now, just for kicks, I'm going to put you on the spot here. Can you tell me which ones actually match that one? Yeah, I know I'm putting you on the spot here, but do you mind?
I don't mind. I just have to find them. I guess
Okay.
6, 7.
6, 7, yes.
9.
I disagree. No, not 9.
So they have to be right next to each other?
Yeah, it has to be an ester grouping on the end. So it has to be C double bond O, 2 carbons away from an ester grouping to be glycine or cross glycine.
Okay, wait. C double bond O, 2 C's away from.
I'm going to throw another one in here too. Okay.
But the Novagal has another characteristic, doesn't it?
Well, the specifically, if I really wanted to do the Novnagle, it would be like this. But that's this is still a subset of that. Specifically, I mean, if you really wanted to be real picky, that's a Novnagle. It's got
Except
the two.
that doesn't look like the picture that it doesn't look like the Aldol picture
Yes, it does.
because it has two.
Yeah. This is like an extra carbonyl group up here, Julie, where I've got the cursor.
Okay.
Yeah, but I wasn't trying to write. Others would be the Michael reaction. So anything that doesn't fall into those two categories would be a Michael reaction.
Like 9.
Like 9, yes. And can you find another one?
12.
12, yes. Any others? No, there aren't any others. All right, that's it, 9 and 12. But if you wanted to classify the glycine, that would be 6, 7, 13. Yeah, 6, 7, and 13. 13 is also glycine. All right, and the aldols, specifically the aldols, 5, 10, 11, and 15. 5, 10, 11, 15. They're all aldols or crossed aldols, and as a subset of those, the Novnagles, which do follow again the same pattern. Novnagles will be 8, the Novnagle. And 14, 8 and 14. Does that answer your question, Julie?
Sort of.
Sort of. Oh.
I know, that's how I feel.
Oh. Do you have another question? Did it help or not? All right. Well, have a think about it. And if you think of something, let me know, okay? We can come back to it if need be. All right, Julie?
Okay, thanks.
Okay. Peter?
Yeah, I haven't made it to the synthesis part yet, but I had questions from the 40, the random ones,
Mm-hmm.
and it was more specific on 28 and 31. I'm still confused on how do you know what goes up in the 3D like drawings.
28. Okay. Oops, sorry about that. Didn't mean to do that.
Seems simple when they're open, but like when they're closed like that, to do the 3D drawing, I'm messing up what's going up.
Okay. So this is 28. Okay, flip that around, do the that, and then you'll do the arrows. Okay. Now this business here is what joins together. I'll show it as 2D as well, I guess. Maybe that will be helpful. Okay, do you agree with the 2D diagram, Peter?
Yes. Yes.
Okay. Now I'll use some different colors here because again, it's really crucial that this kind of helps if you do it this way. I'll do this. This is the one I've been using. Okay. And this becomes this inverted book shape, which means that what I'm pointing to here is going to be the bridge. That's what's going to point up, which looks like this. Put the double bond in there too. And then attached down here on this part, you've got the other part that has the C double bond O's on it. Okay, I mean, that's how you do 28.
That was confusing because the double bond like seemed like it was pointing up in the
Oh, it might be. Sure, but there's nothing
No.
wrong with that. I mean, this is just one way of drawing it, Peter. I mean, if you look at the answer.
Oh, okay.
Sorry.
All right. So I drew it like you did right there.
Right. Well, that's not wrong. That's not wrong. What are we missing? Actually, I'm missing a couple of things here, aren't I? This business here, right?
So just because it's inverted the opposite way doesn't matter.
No, it doesn't matter.
Okay. So that's where I was like, I'm like, I don't get how I'm supposed to get that way.
No,
Like
no, it's okay. I mean, think of it like an airplane propeller. It can be, everything's sort of interchangeable.
All right, that was my biggest confusion.
Okay, I'm sure it's probably the same way for number 31 as well.
Yeah, it was the same exact.
Okay, all right. Okay, any other questions, Peter, about that?
No, those were just the two that were frustrating.
Okay, all right. Okay, other questions from people? Anybody got any other questions about test 4 that they'd like to talk about?
I have another one.
Okay, now Julie, before you ask another question, let's go back to the previous one. Do you still? I know you don't feel good about it, but I don't know.
The previous one is the question I'm going to ask.
Oh, cool. All right.
Good, because it's really the only problem I have.
Okay.
Is number 9 in particular,
Mm-hmm.
which is the Michael.
Yes.
Okay, so I'm looking at it and I say, okay, well, it doesn't fall into those categories that you gave me.
Mm-hmm.
So it must be a Michael.
Yes.
And I look at the 4th position. So I know that whatever it is attaching in the 4th position.
Yes.
Okay, but I still don't see how to break it up into the way it's broken up.
All right.
So
All right.
I
Okay.
still don't.
Let me show you. Now, in a typical Michael reaction, the 4th position it might not be where you think it is.
Okay.
It's this one here. Now this is the part that you break up here. Is this bond between what amounts to the beta carbon and whatever else here. And that's because in a standard Michael reaction, the setup is always going to be something like this. And if we're numbering this, it'd be 1, 2, 3, and 4. So that's why I split that new bond there for the Michael reaction. So the nucleophile then has to be this, and then the alpha beta unsaturated carbonyl compound would be this one. And this is the carbon that gets attacked. 4, 3, 2, 1.
So how do I know, looking at it, that that's number 4 and not something else from the other side? How do I know that it's,
Because if you look at the pattern for the microreaction, that's where the attack always occurs. It's on the carbon, well, you know, the carbon that's next to the alpha carbon or the beta carbon. All right, so we can relabel that too. That's alpha, and that's beta.
okay, thank you.
All right. Okay. Any other questions? Julie, were you okay then with the glycine and the aldols then?
I have trouble with Glycine, but I get it.
Okay.
Michael, I have a little bit more of a hard time with, but
Okay,
that's okay.
all right.
I mean, I understand where it's supposed to be attaching. I just,
Okay.
Yeah.
All right. Okay. Any other questions from anybody about anything for test 4? Any other test 4 related questions? Does anybody have any?
I have a question.
Yes, Mariah.
Could you explain how to determine whether it's going to be cross-glycine or the Novnagle?
Okay. Well, a Novnagle, you mean for this kind of situation or the original starting reagents?
With the starting reagents.
Starting reagents. Okay, so let me go back to, and I'll get a test here. I'm just going to pick a random one, all right? Because both of those, well, I don't know about crossed glycine, but a glycine will just say okay, just in case that happens to be. But we'll look at this, spring 2017. So looking at the reactions here, that's an addition specifically to this carbon. This one here is a microreaction. This one here is a 1,2 addition. This one's a Novnagle, right? And I'll get to that in a second. Okay, right, that's a Novnagle. That's an acyllein aldol, crossed aldol. That's a enamine assisted addition, and there's a glycine there. Okay, so the big difference is, look at the ester groupings. There's always 2 ester groupings involved in a glycine or even a cross glycine. If you look at this example here though, you'll see that this one doesn't have an ester grouping. It's an aldehyde.
Okay, so it doesn't have the alpha hydrogen. Is that all pretty much?
Well, it's an aldehyde or ketone. It's not an ester. In order for it to be a cross glycine, this would have to be an OMe group coming off here as well.
Okay.
I mean, both species. I mean, that's a condition of the glycine, is that it has to be 2 esters reacting with each other.
Okay.
Is that okay?
Yes, thank you.
Okay. All right. Any other questions? Just trying to see how many people we have here today.
Can you do a roadmap question again?
A lot of people haven't got their video on. Trying to hide from me. I don't like that so much. I'm sorry, what's that, Jasmine?
A roadmap problem
Roadmap
from any
problem.
test?
Okay, for me to start. And this one I might do.
Thank you.
All right. Okay, so looking at the entire problem here, I go down to the bottom. I see it's a 6-membered ring that I'm getting. So I know that A and B are going to be 6-membered rings. So the first thing I would do is to draw. Let me move this over here somewhere. So I would start just automatically with the 6-membered ring, and I'd always start with the C double bond O and Viscumi, there we go. And the other one's going to have the same base structure as well. What's going to vary is the location of the groupings that were on the original chain. So my thought is here to take the original compound and I'm going to number it. I number it from one end to the other, which is going to be seven carbons, which means we are looking at 6-membered rings. So the two possible ways that this can join together, and I'll do the first one, it will be 6 to 1. And the other one will be 2 to 7. Now, when I'm doing the numbering, it's always from the alpha carbon on one side to the ester group on the other. That's why I've got 2 to 7 and 6 to 1. Let's look at 6 to 1 first. 6 to 1 would leave the 7 group on the outside. That'd be 6. This will be 1 over here. And then the numbers, the rest of the numbers just go in here. 1, 2, 3. Oh, where are we? Hang on. 3, 4, 5. All right, so then I can put on the rest of these. Let's see, on 3, I've got an ethyl. On 4, I've got a methyl. And on 5, I've got an isopropyl. Going on the 2 to 7, that means the 1 is on the outside. This will be 2 and this will be 7. 6, 5. 4, 3, and let's see, on the 3 I've got the ethyl, on the 4 I've got the methyl, and on the 5 I've got the isopropyl. Okay, so that's the hardest part, Jasmine. Do you understand everything I just did there?
Yes.
Okay, all right. Does anybody have any other questions about this so far? Now, I won't put the reagents in, but the next thing that will happen is that you'll get a propyl group, and that propyl group will go attached to the carbon in between the two carbonyl groups. And then the rest of it just remains the same. So this is mimicking now the acetoacetic ester synthesis that was in the previous problem on the test. Let's see. Okay. Any questions so far? Oops. So the next one is the conversion to the carboxylic acid. And then the last part is the removal removal of the carboxylic acid group. Everything else stays the same. All right, so then the last thing I do is I look at the last thing I see here in the roadmap, and then I try and figure out which one that is. And I can see that this one that's actually here is this one that's on the left side and not the right side. And you can look at the order here. It goes propyl, isopropyl, methyl, ethyl, propyl, isopropyl, methyl, ethyl. So that would be that one there. So the rest of these then can be labeled accordingly. So A, D, and E. D. And A, and B, C, F, and G. All right. Any questions? Especially you, Jasmine, since you asked it. Any questions? Yeah.
G, is the double bond still there? Or what happened?
Yeah, the double bondo, yeah. Yeah, you're right. Thank you. Okay. Any other questions?
Do you have is there a folder with practice ones for these? Because I haven't got to do these yet.
No. No, because it's really based around the acetoacetic ester synthesis and Diekmann condensation. You already know what you're getting, Peter. And you've got 7 old tests there. I mean, I think 7 of these should be enough for you to practice, honestly.
Oh, okay.
I don't know. For some things, you know, especially things I know people do pretty well on the test. If I know they're doing well on it, I don't tend to provide anything extra. I mean, for this one, 95% of people will get it right anyway, because it's really not that hard. All right, other questions about this one, please, or other questions about, well, yeah, about this one specifically. All right, any questions about anything else then? I'll leave the floor open. Jasmine, did I do enough to answer that?
Yes.
Okay, does anybody have any other questions?
Guess my only other one would be the energy diagram because I haven't looked at that one yet either.
Well, I'll do it because you asked, Peter, but really, yeah, it's always better to have looked at something before you ask it, that kind of thing.
Yeah, I just haven't had time to get to them. I'm still working through the 40 initial.
All right. Okay, so we've got a low temperature and a high temperature here. The first thing you want to do is show the products, and you'll have 2 pathways here. That would be A. Specifically, this whole thing's pathway A. And then B. Oops. So this is a resonance situation. And that would be B. Now I'm going to put dotted lines for pathway A and a straight line for pathway B. So that's going to be A. And B is going to look like this. And what we're going to focus on here, I'm actually going to do what a lot of people do on the tests, and you're welcome to do the same, is I'll label these A, B, and I'll label this one C and D over here. All right, so this carbocation would be here at this point. This is for C, and this one is D. If you look at C, it's a tertiary C+, which makes it more stable. And then for D, that's a primary C+. And then down here, we've got the products, and this will be the one I've labeled A and B, and B is more substituted, so it's more stable. So the kinetic, which I'll put up here, kinetic, which has to do with which one has the lowest activation energy. Is going to be pathway A. And what we're comparing here are these two energies here. And then for the thermodynamic, it's about the most stable product, which is B. And that's pathway B. the supposition with pathway A that goes along with that is that if the activation energy is lower, it means that that's a direct result of the intermediate here, which is the carbocation, being more stable. So the fact that this activation energy is lower than this one is a result of the fact that C is more stable than D. And C is more stable than D because tertiary C plus is more stable than primary C plus. And that's everything in a nutshell right there. I'm not sure of it. If you haven't done it, if you haven't done anything with it yet, Peter, I'm not sure if that was that helpful, but that's the complete answer there.
It gives me something to rewatch as I go through it.
Okay.
I have a question about the kinetic and thermodynamic. So will
Mhm.
kinetic always be the lower temperature and thermodynamic be the higher temperature?
Yes. Yeah, the reason for that is because the kinetic has lower activation energy, which means we need a lower temperature to actually get that to go. All right, any other questions? Okay, any questions about anything else on the test here? Any questions about anything else?
Are there certain problems that you notice a lot of people will get wrong that you'd be able to go over, or is it just all over the place?
Well, the main ones that people get wrong are the ones that people don't want to try, and that's the 3D drawings on the Diels-Alder reactions, Anna. That's one I noticed that people just sort of blow off, only because they don't like the 3D diagram, or they don't think they can understand it, or they don't think they can draw it, or they don't think it's worthwhile, or they think, well, it's only a couple of points, so I'm not going to bother even studying that one. I don't know if that's the reason, whatever, but that's just one. That's the only one I really noticed that people tend to get wrong. All the other ones people tend to do okay on, as far as I can tell. I'm not going to say everybody does okay on it, but for the most part, that's the only one that consistently people get wrong. Mainly because they leave it blank though, and not because they've tried. So I don't know. Do you want me to go over some of those, or is that what you?
Yes, please. Can you so I know the Diels-Alder, the 3D ones. Can we do like a simple one and the more complex one? So I'm not sure if the complex one's gonna be on the test.
Oh well, you never know. You never know. It's all a big mystery right now, isn't it? So I don't think I've done these from 2011 and 2016. So I will. Oops, I don't know if I want the key, do I? Sorry. Yeah, I'll find it here. Looks like my chicken scratch. All right, no, I don't want to use the key because it's. Sorry about that. Let's see.
Would downloading the alternate PDF be easier so that you don't run into the issues you have with the images sometimes?
Probably.
Okay.
No more comments from the peanut gallery, please, Donna. I'm just kidding. Just kidding. Do you ever hear that? Is that a common saying here or not?
Yes.
It is. Okay.
Yes.
All right. So let's look at this. This is a 3D, and the reason you know it's 3D is because the double bonds here are in the ring. I don't remember if I've done this one before or not, but I might have. It's possible. Maybe not. I don't know. Okay, so let's look at a 2D for this one first. All right, so that's the 2D. And I always like to do this as maybe I don't like that as much. Okay. I mean, the whole foundation to this is getting a good 3D diagram. Sorry, a good 2D diagram, I mean, sorry. There we go. All right, does anybody have any questions so far? So I'll do the bridge first. The bridge is this business here, and that's going to go off the top. And there's the bridge. Attached to the C double bond C, we've got that's a 4-membered ring, which is going to be in the same plane. And then we've got the other part here that's going to be either pointing up or down. I'll do this one pointing up. There we go. All right, there we go. Any questions about that? Any questions?
Just happy I was doing them correctly. Just didn't match what was in the thing.
Yeah. Okay. Let's have a look at, so Donna, I'm going to humor you and just do it from here. There we go. Oops. So there is a double bond there, but I'll set this up Pac-Man style. And doesn't look like that. Okay. And let's do we'll do the colors again here. I think it's the hardest part is seeing that. I don't know. Maybe people have a hard time with that. I don't know really. Okay, so let's look at the bridge first. And this one I'll have pointing up. I don't know, what do you all think of that?
Looks nice.
Yeah, you like it?
So if I'm fine, the oh gosh, I don't know how to explain it. The part that's pointing up,
Mm,
the,
the bridge or
from the bridge, yeah.
yeah.
Instead of it having laid flat, I had it pointing straight up.
No, that won't work, and I'll tell you why. If that was a double bond, where I'm pointing the cursor right here, yes, it would be flat. But since it's not a double bond, it means it has to point either left or right. Now, whether it points left or right doesn't matter, but it can't point straight up. It's because of the hybridization. If it's flat, if it's sp2 hybridized, it's flat, which means it's got a double bond, because double bonds are flat. But since it's not a double bond, it has to point one way or the other. It's sp3 hybridized. It's for the same reason. It's for the same reason, Anna. This has to point either up or down. This business here, that either has to point up or down, because that's not on a double bond either. Is that clear, Anna?
Yes, thank you.
Okay. Any other questions? Yeah, if you drew it straight up, I'd mark it wrong. That's true. It's not really, it doesn't sound fair, does it? Yeah, it's true. Any other questions? Okay, other questions about anything on the test? Anything at all? All right, look, if nobody has any other questions, I'm going to leave it here, but what are we doing? All right. Okay, well then I'll leave it here for the day. If anybody has any questions, you can email me. And I guess best of luck on Tuesday. Same story as before.
Thank
All right.
you. Thank you very, very much.
Thanks, everybody.
Thank you, Dr. Musgrave.
All right, bye.
Thank you.